Okay, so we're going to continue on from here and go on to the next practical exercise. Oh, I should have mentioned that practical exercise number 2 that we had was problem number 3. This practical exercise number 3 is problem number 7 at the end of the chapter. And what's the intensity of a traveling electromagnetic wave if B sub m is 1.0 times 10 to the minus 4 teslas? Okay. Now the first thing is that the intensity is the average of the pointing vector, right? And so that is going to be given by C, this value squared, divided by 2 and the permittivity constant, isn't it? So the I, the intensity, is that pointing vector average, speed of light, that magnitude of the magnetic field squared, divided by 2 times this permeability coefficient. So 3.0 times 10 to the 8 meters per second, 1.0 times 10 to the minus 4 Tesla squared, 2, this right here, in terms of henries per meter, is 1.26 times 10 to the minus 6. Okay, so you have to make certain you have the right type of units for this particular value, and that is not supposed to be squared. Okay, this right here is a mistake. You're not supposed to have that there. And when you do that, it turns out the answer is 1.19 times 10 to the 6th watts per square meter. And if you put that in scientific notation, it's 1.2 times 10 to the 6th watts per square meter. Okay? So yes, do not, this right here does not belong there. Okay? Practical exercise number 4. And this is problem number 8. Assume, unrealistically, that a TV station acts as a point source broadcasting isotropically at 1.0 megawatts. What is the intensity of the transmitted signal reaching Proxima Centauri, the star nearest our solar system, 4.3 light years away? Okay? So a light year is the distance the light travels in 1 year. And that is approximately 9.46 times 10 to the 15th meters. Okay? And so R is 4.31 light years. And so it's going to be 4.31 times 9.46 times 10 to the 15th meters. And again, these things are located in the constant section at the back of the book. And the power here is 1.0 times 10 to the 6th watts. Yeah, that's much greater than any TV station would ever be allowed to broadcast. So here, the intensity again is now given by the power divided by the 4 pi r squared, right? So here we do have a squared down there. It's 1.0 times 10 to the 6th watts, 4 pi, 4.3 light years. And as I mentioned, it's 9.46 times 10 to the 15th meters per light year. And this whole thing right here is squared. So the intensity of that signal, when it finally reached there, would be 4.8 times 10 to the minus 29th watts per square meter. The next one, this is practical exercise number 5, and this is problem number 16. So you can see that there's a lot of really good ones that you can do with these equations. Frank D. Drake, an investigator of the SETI, or Search for Extraterrestrial Intelligence program, once said that the Large Radio Telescope in Arecibo, Puerto Rico, can detect a signal which lays down on the entire surface of the Earth of a power of only 1 picowatt. So the question is, what is the power that would be received by the Arecibo antenna for such a signal? And the antenna diameter is 300 meters. What would be the power of an isotropic source at the center of our galaxy that could provide such a signal? Now, what you can't read at the bottom there is the galactic center is 2.2 times 10 to the fourth light years away, and a light year is the distance that light travels in one. So you use the same information you had in the prior one, right? So here you're looking for the power, so you just rearrange that prior equation. So it's P equals I equals, okay, it's 1 picowatt. D equals 300 meters. And the PR is the P of the power received is the power here at the Earth, the area of the antenna, area of the Earth, right? So it's that ratio right there. So here is your 1 picowatt of power that's being received from that signal. Here is the area of the antenna. Here is the portion of the Earth, right? So it's pi d squared over 2. In other words, radius squared, because we were given the d. And so that would be 100. Just a second here. They say 300 meters, but I do believe the diameter is 300 meters. So this d, this should be this divided by 2, shouldn't it? Yes, it should. Okay. And this is, no, as a matter of fact, what they did is they took that 4, the squared value there, and multiplied it by this to give you the 16 here. Okay. So they did use 300 meters here and put this into the denominator here. I remember how they did that now. Okay. The pi's will cancel out, and here you have the radius of the Earth again, and all of this right here squared. Once you do that, you'll get 1.386 times 10 to the minus 22nd watts, or 1.39 times 10 to the minus 22nd watts. Okay. Now I got 1.39 there because this is the incorrect number of significant figures. Now, then what is the power? What's the source of the power? Okay. For them to do that, we have to go back to the other equation and do the power equals 4 pi r squared, the intensity, right? So that's 4 pi, and this is the number of light years away. This right here is the number of meters per light year, and all of this is squared. And then you have the intensity here, 1.0 times 10 to the minus 12th watts divided by 4 pi, and then the permittivity constant here squared. Okay. And when you end up doing that, I got 1.1 times 10 to the 15th watts. Okay, the power equals 1.1 times 10 to the 15th watts. That's how strong that signal would have to be. So, continuing on, let's talk about radiation pressure. This is an interesting area because this is what so many of the space programs have thought would have to be the source of power for any intergalactic type of spaceship, right? So everybody who the radiation pressure is the surface, when a surface intercepts that electromagnetic radiation, a force and a pressure are exerted on the surface. If the radiation is totally absorbed by the surface, the force is that intensity times the area divided by the speed of light. If the radiation is totally reflected along its original path, the force is twice that, 2IA over C. Okay? So the radiation pressure is the force per unit area, with total absorption, PR equals I over C. Or in the other case, for total reflection, it would be PR 2I over C, right? Total reflection back along the path. So let's think about this. The light of uniform intensity shines perpendicularly on a totally absorbing surface, fully illuminating the surface. If the area of the surface is decreased, do A, the radiation pressure and the radiation force on the surface increase, decrease, or stay the same? Okay. Now the radiation pressure is already per unit area. So that is going to stay the same, isn't it? The radiation force, however, because you no longer have that, you have a different one, is going to be a decrease in that radiation force, right? You can see essentially all they're doing is just asking you about how does area figure in to into a pressure calculation versus a force calculation. Now we'll go on to the practical exercise number 6. Let me see. This one is problem number 20. So the radiation from the sun reaching the Earth just outside the atmosphere has an intensity of 1.44 kilowatts per square meter. Assuming that the Earth and its atmosphere behave like a flat disk perpendicular to the sun's rays. I know, all the flat Earth people are going to be really happy with that part, aren't they? That all the incident energy is absorbed. Calculate the force on Earth due to the radiation pressure. And for comparison, calculate the force due to the sun's gravitational attraction. Now the equation that we need to use there is the same intensity, force of radiation is that PR, the pressure, times the pi, radius of the Earth, squared, right? So it's going to be the intensity divided by the speed of light times pi, the radius of the Earth, squared, okay? So that would be the radiation pressure. So let's see how they work this out. And so yes, they have the force of the radiation is that pressure of the radiation times the pi radius of the Earth squared, or I over C. So this pi is pulled out there. Intensity is 1.4 times 10 to the third watts per square meter. The radius of the Earth, 6.37 times 10 to the 6th meters squared. And then the speed of light, 3.0 times 10 to the 8th meters per second. I get 59.46 times 10 to the 7th newtons, or actually 5.9. It's 59.46. You should not round 46 up to 60, right? So it should be 5.9 times 10 to the 8th newtons. Now, the gravitational pull of the sun on the Earth is our famous equation that we have from Newton. The gravitational constant, mass of the sun, mass of the Earth, the distance, this is not a diameter, this is the distance between the Earth and the sun squared. So this is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. The sun has a mass of 2.0 times 10 to the 30th kilograms. Earth has a mass of 5.98 times 10 to the 24th kilograms. And it's divided by 1.5 times 10 to the 11th meters squared. That's the distance, right? And so I did get the same number that they did of 3.6 times 10 to the 22nd newtons. Let's end there and we'll start the next section with polarization.